So before we start with the actual chapter, let's first revise a few terms, a few concepts related to circles. Okay. So this figure, this shape that I've drawn, as you all know, this is a circle, right? Now, there are three, you can say that a circle divides the plane. This is a plane, right? The sheet or the screen, or if I have drawn it on a whiteboard, then the board is a plane. If I draw it on a paper, then the paper is a plane, right? So here, this screen is a plane, and this circle is dividing the plane into three parts. Three parts. One is the exterior of the circle. Okay, everything outside the circle is the exterior of the circle. Okay, this entire thing is the exterior of the circle, everything. This is the exterior of the circle. And then there's the interior of the circle. Can someone tell me what is going to be, what do you think the third part of the plane is? One is the exterior.
Outline,
Sorry.
the borders,
Very good. The boundary.
the borders,
Yeah, the border, the boundary. So the other is, the third part is the boundary of the circle. Okay. So we can say that a circle divides the plane into three parts. What are those three parts? Exterior, boundary, and interior. All right. So basically, if there is any point at all, if any point that I draw on this entire screen, any point, let's say this point. So any point is going to lie in one of these three regions. Okay. It is either going to lie in the exterior or in the interior or on the boundary. So for example, if I put a point here A and I ask you where is it, you will say it's in the exterior of the circle. If I put a point here, let's say B, you're going to say this is in the interior of the circle. If I put a point over here, C, it is on the boundary of the circle. Okay. So these are the three things. Now, let's talk about within a circle, what are the different points? Okay, first of all, what is a circle? Does someone know how you can define a circle? Like, we know that a lot of things around us are circular in shape, right? A lot of things. And in fact, it is one of the most, you can say, easily formable, easily drawable images. It takes little to no effort. How can you define a circle?
the center is called the radius, then
Can you repeat?
the center is called the radius.
Okay, so you are saying the circle has a center, and you said something about radius. We will just get into that. What is the radius and why it is such a special thing? Okay, so a circle is that figure, that shape, whose every point is at an equal distance from the center. Okay, I'm giving a very rough definition. Circle is that figure, a figure or a shape whose every point, whose each and every point is equidistant from the center. What does this mean and why is it so special? I mean, why is there an entire chapter based on circles? Right? So, see, the special, why this particular property is special is, see, if you take, for example, a square, right? If you take a square, then if you take the center of the square and if you start measuring the distance of each point, we know that every figure, if you talk about even a line segment, it has infinite number of points. It is made up of infinitely many points. When you join all these points together, you get this line segment, right? Similarly, a circle is also made up of infinitely many points. If someone asks you how many points are there on a circle, the answer will be infinitely many points. Similarly, on a square also, there are infinitely many points. Now, let's consider this point. Okay. This point will be the distance between this point and the center of the square is this thing. Some distance. It could be anything. Or if you can say if this is the side called A, if the side of the uh, square is A, then this much will be A by 2, right? Because this is exactly the center. That's why this is going to be A by 2. And similarly, this one will also be A by 2. Yeah, we'll come to that a little later. Now, if I talk about this point, the distance of this point from the center of the square, is it the same as the distance of the other point? Let's name this point as P and this point as Q, and the center, let's name it as O. So is the distance between P from the center and the distance of Q from the center, are those two the same distance? Like, is it equal? What do you think? It's not
Ma'am,
equal.
no.
Yeah, good. It's not equal because you can see that this is at a longer distance, right? The distance is more of P. The distance of P from the center is more. In fact, if you want to calculate it, how much it is precisely, see this one is also A by 2. Yeah. So this is going to be, you can see this is a right angled triangle. So if you want to find the distance of OP, the distance PO, it's going to be under root a square by 4 plus a square by 4. How am I getting this? Pythagoras theorem, if you remember. A by 2 whole square plus a by 2 whole square, right? When you have a right angled triangle, the hypotenuse square is equal to the sum of the squares of the other two sides. So this is equal to under root a square by 4 plus a square by 4, which is 2a square by 4, which is a by 2 root 2. Or you can say a by root 2. Okay, so this is a different distance. So this distance is going to be different, and that's why you can see that every single point on the square, it is at a different distance. The distance is not the same. Okay, so the square doesn't have the special property, only a circle has that special property. So that is why a circle is a special figure whose each and every point is equidistant from the center. Okay, so what did we learn from this? This point, the center, is that point which is equidistant from every other point. Okay, so if you want to see what is this distance is called the radius, and the radius is going to be the same no matter which point you choose on the circle. So the radius is going to be the same. Okay, if this is P, OP is equal to OQ, that's the radius. All right. Now, in this chapter, we're going to be talking a lot about something which is called, let me make it first, something which is called a chord. This is still too light. Yeah, something which is called a chord. A chord. Let's call this AB. So here AB is called CHORD, chord. Like, you know, how you have chords on a guitar. So AB is a chord. Definition of chord. Let's see what a chord actually means. How can you define it? A chord is a line segment joining any 2 points on the circle. And remember, this is on the circle. If you have a point inside the circle, let's say a point X, and you join it with a point on the circle, let's say a point C, then this CX, the line segment CX, is not a chord. It's not a chord. Why? Because chord is a line segment joining any 2 points on the circle. So the 2 points have to lie on the circle. So that's a chord. Acha. How many chords can a circle have? Can someone tell me? How many chords do you think a circle can have?
Ma'am, like many can
Yes, many. How many? That's right, many. You're on the right track. So a circle has infinitely many chords. Similarly, it has infinitely many radii. Yeah. You can draw a radii from here to here, from here to here, from here to here, here to here, here to here. You can draw as many as you like. So that means it has infinitely many radii. It has infinitely many chords. Okay. Now, so see here you can draw many chords. Let's say this is also a chord. Yeah. This is going to be another chord. Let's say CD. Okay. Similarly, you can draw a chord like this. This could be X, Y. Okay. So you can draw as many chords as you like in any direction. It just has to join two different points on the circle. Now my question is, what do you think will be the longest chord of this circle? The longest chord.
the diameter.
Sorry?
Ma'am, the diameter.
Yes, the diameter is the longest chord of the circle. Why? Because if you see, I'm just going to raise this a little bit. Okay. So this is also a radius. I'm going to draw the diameter now. So this is the diameter. Yes. And we know that the diameter, so PR is equal to diameter. And there's not just one diameter. Just like there are infinitely many radii, there are infinitely many chords. Similarly, there are infinitely many diameters. And diameter is twice of the radius. Diameter is twice of the radius. Or you can say radius is half of the diameter. And I think you can see now why we say that diameter is the longest chord. Diameter is the longest chord. Because just think about all the other chords that you can make, all the other chords that you can make like this, they're all going to be shorter than the diameter, all the other chords. Okay, if you make a little above the diameter, that's also going to be, they're all going to be chords, but they're going to be shorter than the diameter. So you can say that the diameter is the longest chord of the circle. Oops. Okay, always remember this point because this is going to come in handy, the longest chord wala point. Okay, now a chord, if you forget about all of these other things, a chord divides the circle into two areas, into, you can say, into two different regions, this portion and the rest of the circle, right? So this portion is what is called a segment. It's called a segment. Okay, this portion is called a segment. In fact, not just this portion, but the other portion as well. This one. This portion is also a segment. This is also a segment. This is called the major segment. Okay. So what did we learn here? A chord divides the circle into two regions called segments. I hope you're all writing this down alongside. A chord divides the circle into two regions called segments. One of them is going to be a major segment, and one of them is going to be a minor segment. Major, obviously, it means the bigger one. Minor means the smaller one. So if you want to define what a segment is area or region between chord and arc of the circle. Now, what is this arc? Okay, segment is region between the chord, this chord, and the arc of the circle. This is the arc. We write it as, for example, if you want to talk specifically about, just a minute. If you want to talk specifically about this particular region, I think I should. Yeah. So if you want to talk about this particular region, this is called an arc. Okay. And you will write it like this. You will write it like arc AB because it's from A to B, right? Or you can say minor arc AB because it's the smaller arc. There's, if you just write arc AB, it could also be the arc going from A, from this point, like from here, all the way, all the way, all the way till here. So this is also an arc, but that is the major arc. So this one is the major arc. This is called the major arc. So again, this is the major arc. Major arc AB. Why AB? Because the starting point is A and ending point is B. And why major? Because it's the big one. The small one, we have already written it as minor arc AB. Okay. So if you want to think about it like this, what is an arc? Your circle, if your circle is like this, and if I erase this portion of the circle, and I just, oops, sorry. I just make it like this. Okay. So this, both of these are your arcs. Okay. This is the minor arc and the yellow one is your major arc. Similarly, you have a major segment and a minor segment. Okay. So once again, what is a segment? It is the region between chord and arc. So if it is the region between the chord and the minor arc, then it's called a minor segment. If it's the region between chord and the major arc, then it is called the major segment. Just some technicalities. Okay. All right. Now let's talk about something which is called, and you might have heard this word a lot in your daily life as well. It's called a sector of the circle. Okay. Like you must have heard, in localities, in cities, in towns, you must have heard sector this, sector that, right? So, yeah. Uh, okay. Okay. So this area is called a sector. The area that looks like a pizza slice, okay, or a slice of pie. This is called a sector. And what is the definition of sector? Definition of sector: area or region enclosed by two radii and an arc. So it's the region enclosed by two radii. Radii is the plural of radius. Region enclosed by two radii and an arc. So this is the sector. Similarly, you have minor sector and major sector. So this, the pink color one, is the minor sector, and this one, the lavender color one, or let me just change the color. Yeah, the blue color one is your major sector because it is enclosed by the same two radii, but the major arc. Okay, so this one is your major sector. Okay, so you can say if there are two radii, they make something like a pizza slice. This becomes, this divides the entire circle into a major sector and a minor sector. These are just some technical terms which we needed to know in order to proceed. Okay. Acha, just one more technical term. See, if you have a circle, and I think you all should get used to drawing uh, a little, neat and tidy circles, because in this chapter we're going to draw them a lot. If you have a chord, let's say a chord, this chord AB, and a point over here, let's say P. This chord is said to subtend an angle at the point P. Okay. This angle is called angle subtended by AB at point B. Okay. I'm going to write it here. Angle APB. This is called angle APB. This is angle subtended. Angle subtended. Sorry. Subtended by chord AB at point P. Okay. So this is a term that you guys need to get comfortable with. Angle subtended by something. Okay. So I am going to just make sure, I'm going to try to make sure that you guys have understood this concept of angle subtended by a chord. Okay. So let's say we have another circle here. This is the center. I am drawing a chord here and a chord here. Don't get confused with all the lines. It will all start making sense in a little while. Okay. Uh, I think this much is enough. Okay. So this is a chord AB. the black chord AB, and this is a chord CD, and this is a point P, this is a point Q. I want you to tell me, let me draw a few. So this is angle 1, angle 2, and angle 3. Just a minute. You don't have to draw this. I'm just, it's a small test kind of thing. Yeah. So here we have the center of the circle. Okay. Now tell me angle subtended by chord AB at point P. Which one is it? You can name it like this. You can name it as angle this, angle this, the way we write it. Or you can just say angle 1, angle 2, or angle 3, whichever it is. Okay. Angle subtended by chord AB at point P. Which one is it?
Like we should tell another like this.
No. You should tell me which angle it is. See, there are plenty of angles over here, right? To make things easier for you, I have just named the angles, angle 1, angle 2, and angle 3. And I have given them different colors so that it's easier for you to identify. I'm asking angle AB, over here, we saw that the chord AB was subtending an angle at a point P, and that was this angle. We named the angle, right? So similarly, what you have to do over here is you have to tell me what is the name of the angle subtended by this chord AB. Let me highlight the chord for you. This chord AB at point P.
Angle 1.
Very good. It's angle 1, or you can say angle APB, right? It's angle 1 or angle APB. Good. Now, angle subtended by chord AB at point Q. Which one is it? Look at AB and look at point Q. And see, first look at AB, then immediately look at point Q and tell me what is the angle that comes in your field of vision. When you are first seeing
AQB.
AB, very good, angle AQB or angle 2. Okay. Now the last one, angle subtended by CD, the chord CD at point Q. This is
Angle CQD or angle 3.
very good. Very good. This is angle CQD or angle 3. Okay, so I hope by now you've understood what this angle subtended by it means. Okay. Acha, by the way, one tiny thing. If I remove the chord over here, okay, and we are left with the arc CD. You can see the arc CD, this arc over here, uh, this arc over here, arc CD. Okay, so instead of angle subtended by chord CD, if I say angle subtended by arc CD, it is the same thing. Okay, angle subtended by the chord, whether it is the chord CD or whether it is the arc CD, same thing, not going to make a difference. All right, so sometimes we are going to use the
Okay.
chord, sometimes we are going to use the arc. So that's why I just thought I'll just point it out to you. All right. Now let's come to some of the questions. We'll start with basic questions. Okay, so this is a theorem. The theorem is equal chords of a circle subtend equal angles at the center. So what is this trying to say? It's trying to say that if you have a circle and you have any two chords which are equal in length, let's say this chord and this chord, two chords that are equal in length, then the angle subtended by them at the center, this is the center, okay, this angle over here and this angle over here. So let's say we have two chords AB and PQ. So first of all, when we have questions like this, to prove that type of questions, we need to write what is given and we need to write what is asked of us. Okay. So given equal chords, equal chords are given. That means AB is equal to PQ and that's it. Okay. And also that O is the center. I mean, it's kind of obvious. You don't have to write it in your exams, but just for this one question, I'm writing it over here. Okay. Now, equal chords of a circle subtend equal angles at the center. You have to show that. TST means to show that. They subtend equal angles at the center. What angle is AB subtending at the center? It is subtending this angle AOB. So to show that angle AOB is equal to angle POQ. This is what we have to show. So does anyone have any idea how to go about with this? So we can show both of these triangles as congruent. If we can show them as congruent, then by CPCT, we can show that the two angles are equal, right? So think about it. How do we prove these two triangles as equal? As congruent. You've already done the triangles wala chapter, right? So you know how to prove two triangles as congruent. So you'll say in solution.
AB is equal to PQ and O
Hmm.
is common.
What is common? O is a point. So, but what does that give us? O is common. So what? One
AO
first
and
thing you said
OQ.
is AO and OQ.
They are radius.
Very good. So AO is equal to OQ, or you can say AO is equal to PO if you want, or okay,
Yes,
OQ is
ma'am.
also fine. All of them are equal because they are radii, right? They are radii of the same circle. So obviously they will be equal. Radii of the same circle. Okay. And then similarly, the other side as well, this one. OB is equal to OP, radii of the same circle. Therefore, triangle AOB is congruent to triangle POQ. I think you should say QOP in this case. QOP. By which congruence rule?
SSS.
Very good. By SSS rule. Therefore, these two angles which we were talking about, angle AOB is equal to angle POQ by CPCT. Hence proved. Okay. Let's prove now the converse of this theorem. Converse means, so see, if A then B, if A could be any some condition over here, the condition was for these two chords to be equal, right? If A then B, the converse of this statement is if B then A. Okay. What this means is, here we are saying in this theorem, equal, if two chords are equal, then the angle subtended by them at the center will be equal. In the converse part of it, we say if the angle subtended by any two chords are equal, then these two chords will also happen to be equal. Okay, so converse part. Okay, so if the angles subtended by two chords of a circle at the center are equal, then the chords are also equal. And you can prove this in a very similar way. I'm just going to copy, oops, I'm just going to copy this. Okay, so yes, now who will tell me how are we going to proceed? First, let's write what's given. Let's write what's given. Given the fact that the angles subtended by them are equal, meaning angle OAB and angle POQ are equal. Angle OAB is equal to angle POQ. To show that the chords are equal, meaning to show that AB is equal to PQ. The same thing we have to do. But in this case, the congruence rule will become a little different. Yeah. So in triangle AOB and triangle QOP, again AO is equal to QO because radii of the same circle. Then similarly OB is equal to OP, again radii of the same circle. And angle AOB is equal to angle P or QOP. Reason given. Therefore, by dash rule, triangle AOB is congruent to triangle QOP. By which rule?
SAS.
Very good. So by SAS rule, these two are congruent. Therefore, AB is equal to PQ by CPCT. And we're done. This theorem is called perpendicular from center to chord bisects the chord. This is the short form of the theorem. I am just going to write the long one. Perpendicular from center of circle to a chord bisects the chord. So here we have a circle, we have the center, and we have a chord. They are saying perpendicular from the center of the circle to the chord. So if our chord is AB and we draw a perpendicular from O to AB, this perpendicular is going to bisect the chord, meaning it is going to divide AB into two equal parts, AM and BM. So let's write what is given. Given the fact that it is a perpendicular, yeah, OM is perpendicular to AB. This is given to show that AM is equal to BM, which in fact is equal to half of AB. Okay. If you want, you can draw this as a straight forward figure as well. If you want, you can draw it like, let me just draw it roughly. If you want, you can draw it like this as well. This is your chord. This is the perpendicular. This way it will be easier for you to, keep track of things. If you want, you can draw it like this as well. Okay. All right. Let's get started. So solution. Try making this into a triangle. Okay. So here we have two triangles. In triangle OAM and triangle OBM. So see, we need to show that AM is equal to BM. So in order to show that, we can just prove that these two triangles are congruent. If we prove them as congruent, then these two sides, we will be able to prove them as equal. So let's try to prove them as congruent. So again, three things are needed. Yeah, who will tell me? Yeah,
AB is the chord.
AB is AB is the chord, yes. To show that AM is equal to BM, we need to show these two triangles as congruent. To show these two triangles as congruent, we need three things. What three things can we use here? If you want, you can try rotating the screen a little bit, if possible. See, OA is equal to OB because radii of the same circle are equal. Then OM is equal to OM because it's common. It's a common side, na? OM, common side. Then angle OMA, this angle is also 90. And the other angle, angle OMB, this is also 90, given. Therefore, triangle OAM is congruent to triangle OBM by which rule? By which rule?
RHS.
Yes, very good. R, right is this one, right angle. Hypotenuse is this one. And one of the sides is this one. So RHS. by RHS rule. Therefore, AM is equal to BM by CPCT. Hence, we are done. Next, theorem 4 is the converse of the previous theorem. Can you guess what the converse will be? See, over here it was given. What was given? Given was the fact that it is perpendicular to show that it bisects. Hmm? Now, in the converse, it's going to be the opposite. It will be given that there is a line from the center which bisects the chord. You will have to show that that line is in fact perpendicular to the chord. So let's write it. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Okay. Now we'll draw our circle. We'll draw the center. And we'll draw a chord. We know that this line OM, we know that it bisects the chord. That's what we know. We have to show that it is perpendicular to the chord as well. Okay. So, given AM is equal to MB, right? The line drawn through the center of a circle to bisect a chord. Yeah. So, it's already given to us. Is perpendicular to the chord is what we need to prove to show that OM is perpendicular to AB. Okay. Similarly, the same way which we did the previous one, consider these two triangles and show them as congruent. In triangle OAM and triangle OOOBM. OA is equal to OB reason, radii of the same circle. OM is equal to OM reason, common side. AM is equal to BM given. Okay. So therefore, by SSS rule, triangle OAM is congruent to triangle OBM. Therefore, by CPCT, this angle over here is going to be equal to this angle over here, which is angle OMA is going to be equal to angle OMB. But we haven't yet proved that this is equal to 90 degrees. So what are we going to do? We're going to say that these two angles are a linear pair, right? So if you can call them X is equal to X, say. Let's call it X. Say it is X. So then what happens is, since angle OMA and angle OMB form a linear pair. Therefore, angle OMA plus angle OMB is equal to 180 degrees. And we have taken them to be equal to x. So that means x plus x is equal to 180 degrees. That means twice of x is equal to 180 degrees. That means x is equal to 180 by 2, which is 90 degrees. So that means angle OMA is equal to 90 degrees is equal to angle OMB. And that shows that OM is perpendicular to AB. Okay. Done. Shall we move forward?
Yes, ma'am.
Okay. So, now next theorem, theorem 5. Equal chords of a circle are equidistant from the center. So, in the first theorem, we proved that equal chords subtend equal angles at the center, right? But here we are going to prove that equal chords are equidistant from the center. So this theorem is talking about one circle where there are two chords which are equal in length. Okay, there are two chords, could be anywhere in the circle, doesn't matter. They are equal in length. Their distance from the center is the same. What is the distance from the center? See, if you have 2 points, now pay close attention to this. If you have 2 points, distance between those 2 points is simply the shortest distance between them, right? It could also be this, but you don't say this arc is the distance between the 2 points. Why? Because we say that the shortest one is the distance between 2 points. What if it's a point and a line? The distance between a point and a line is the shortest distance. See, you can say it is this distance, you can say it is this distance. Yeah, you can say it is this distance, this distance. So the distance between the point and, let's say, this line L happens to be this thing, the distance which is perpendicular, the line segment which is drawn perpendicular to the line L. Okay, so this is called, if you name this as PA, so this PA is actually the distance between P and the line L. These other line segments are not the distance between them. Okay, so the distance between this chord and the center the distance between this chord and the center is that one which is going to be perpendicular to it. So they are saying this distance is equal to this distance. That is what we need to prove. Acha, by the way, this could also mean if there are two different circles, but they are congruent circles, meaning that they are both of the same radius and they both have two different chords which are equal. Then this distance, let's call it OM, and this distance ON is going to be equal if these two chords AB and CD are equal. Okay, and that is for two congruent circles. Doesn't have to be the same circle, it can be two different circles, but have to be congruent circles only. Okay, so anyway, let's get on with the proof. So let's call it O, A, B, C, D, and let's call this as M, let's call this N. Okay, now what is given? Given the chords are equal, meaning AB is equal to CD, to show that OM is equal to ON. Okay, so how do we show this? You can take this triangle and this triangle if you want. Okay, you can take any of these two triangles. So solution: in triangle OMB and triangle OND, OM, sorry, OB is equal to OD because radii. Yes. MB is equal to ND. Why? Because since AB is equal to CD, therefore half of AB is equal to half of CD. Yeah, AB is equal to CD is given. AB is equal to CD given. So half of AB will be equal to half of CD, and half of AB is what? MB, and half of CD is what? ND from previous theorem. Okay, that is why MB is equal to ND. And the third thing is angle OMB is equal to angle OND is equal to 90 degrees, because we know that since this is a perpendicular, right? Because it is the perpendicular from center to chord. Okay, so since it's perpendicular from center to AB, so it's 90 degree. Perpendicular from center to CD, so again 90 degree. So here we have used, this is side, this is angle, and we have used, okay, we have used a different result, AS. Okay, so I think we should just leave it at this right now. Don't write further. Okay, we will come back to this because a few adjustments we have to do in this. Okay, so just leave it at this since our time is over and there'll be students joining for the next class. So this theorem we will finish in the next class. Okay. Acha, one more thing before I forget. Uh, After this class, please attempt. There's a 5 minutes test which has been uploaded on the portal, which is related to today's class only. So please attempt that